Lanthanoids. General symbol for any lanthanoid is Ln, also known as 4F series. The elements are 14 elements. Cerium atomic number 58 to lutetium atomic number 71. These are the elements that come after lanthanum. Hence the name lanthanoids. The chemistry of lanthanum also studied along with the lanthanoids. The general electronic configuration of lanthanoid 4F1 to 14, 5D0 to 1, 6S2. This is the general electronic configuration. 6S2 is common, 5D with a 0 or 1 electron. 4F orbitals are filled with electron. That is 4F1 for cerium, 4F14 for lutetium. So F atomic orbital, if they are empty, half filled or completely filled, the configuration is stable. So europium with the 4F7 electronic configuration, ytterbium and lutetium with the 4F14 completely filled F orbital configuration. This is half filled F atomic orbital configuration are extra stable. Now the most common oxidation state of lanthanoid is, all lanthanoids show a common oxidation state of +3. And in the +3 state, they have electronic configuration 4F. Lanthanum 3+. So the lanthanoids are lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. 14 elements. This is lanthanum is 15th one, so total 15 elements including lanthanum. Most common oxidation state of lanthanoid is +3. In +3 oxidation state, the lanthanoids have a configuration 4F(n), where the number of electrons in F atomic orbital vary from 1 to 14. Lanthanum 3+. Lanthanum 3+, the configuration is 4F0. This is not a 4F series element, it is not a lanthanoid, but it is also studied along with the lanthanoids. 4F0, cerium 3+. Cerium 3+ has got a configuration 4F1. Praseodymium 3+ has got a configuration 4F2. 4F3 for neodymium 3+. Promethium 3+, 4F4, 4F5, 4F6, 4F2, 4F3, 4F4, 4F5, 4F6, and for gadolinium 3+, the configuration is 4F7, that is extra stable, half filled 4F. Then 4F8, 4F9, 4F10, 11, 12, 13, 14. Lutetium 3+. Lutetium 3+ is also extra stable due to 4F14 electronic configuration. So when we compare the atomic and ionic size of lanthanoids from left to right, from lanthanum to lutetium, we get the graph. The ionic radius of lanthanoid 3+ ion plotted against the atomic number. Means along a lanthanoid series, how the atomic and ionic radius vary. The ionic radius, we can see a steady decrease with the increasing atomic number. When the atomic number increases from left to right along a lanthanoid, there is a steady decrease in the ionic radius, right? Ionic radius of lanthanoid decreases from lanthanum to lutetium. This steady decrease in the atomic and ionic size of lanthanoid from lanthanum to lutetium is called lanthanoid contraction. What is lanthanoid contraction? The decrease, a gradual decrease in the atomic and ionic size of lanthanoid from lanthanum to lutetium. Now, what is the cause of lanthanoid contraction? Why there is a steady decrease in the atomic and ionic size? It is due to the poor shielding effect of F atomic orbitals. F atomic orbital compared to sp d orbital, the shielding effect of F atomic orbital is very poor. they are poor shield. They cannot shield the outer electron much from the nuclear attraction. So the outer electrons experience more effective nuclear charge and hence more nuclear attraction. So the atomic and ionic size decreases. What are the consequences of this Lanthanoid contraction? There are 3 consequences. First one, similarity in the properties of 4D and 5D transition elements. 4D and 5D series transition elements have similar properties. That is, second and third transition series, 4D and 5D series have similar properties. This is due to Lanthanoid contraction. These elements 4D and 5D series have almost similar size and hence similar properties. So that makes their study difficult. Then another consequence of Lanthanoid contraction is separation of lanthanoids. Separation of lanthanoids is possible due to lanthanoid contraction, because lanthanoids resemble in their property than any members of transition elements. Lanthanoid elements from lanthanum to lutetium resemble to one another in their properties. Their properties are more closer than the properties of transition elements. So because of similar properties, their separation is very difficult. Because of lanthanoid contraction, their properties vary slightly. Because of this change in the atomic and ionic size, their properties of lanthanoids vary slightly. That make their separation possible. So separation of lanthanoids is possible due to lanthanoid contraction. Only because of lanthanoid contraction, their properties vary slightly and they can be separated. So the slight variation in the properties is utilized in the separation of lanthanoids. Now the third consequence of lanthanoid contraction is decrease in the basic strength. Decrease in basicity of lanthanoid hydroxides. Lanthanoid hydroxides are basic in nature. When we compare the basicity from left to right, from lanthanum hydroxide to the last lanthanoid, lutetium hydroxide, the basicity decreases. Along a lanthanide series, the basicity of the lanthanoid hydroxide decreases. This is due to lanthanoid contraction. As a result of lanthanoid contraction, atomic and ionic size of the lanthanoid decreases. When the size of the lanthanoid decreases, that is lanthanum +3 to lutetium +3, size decreases. Smaller the cation, greater the covalent character. As the size of the lanthanide 3+ ion decreases, covalent character increases. Fajjan's rule. Smaller the cation, larger the or greater the covalent character. Covalent character increases, ionic character decreases. So the concentration of OH minus ion produced in the solution decreases. Basicity decreases along a lanthanoid series. That is, lanthanum hydroxide is most basic and lutetium hydroxide is least basic. What is lanthanoid contraction? What is the cause of lanthanoid contraction? What are the consequences? Very important.